Hello friends, in this video I will discuss the application of the Schrodinger equation, and one example is particle in a box or infinite potential well, and I will discuss the Schrodinger wave equation for particle in a box and then the tunneling phenomena. We can see that if a particle is inside this box of length L, then it is confined from 0 to L in this box, and according to classical physics the particle can exist anywhere inside the box and it should follow the Newton's law. But according to quantum physics it will have some certain states inside this box, and we can see here from this image that the particle is bouncing back from the walls of this box, and quantum mechanically it will have this standing waves inside this, and according to de Broglie we can find out the wave function for this this matter wave, and this is the wave function or we will get using the Schrodinger wave equation. Now we will use the Schrodinger equation to find the wave function and energy of this particle which is inside this box. And if we consider a particle of mass m which is moving along x direction only from x equal to 0 to L, and the particle is free inside this box, means potential energy B or U equal to 0, and the walls are infinite high and the potential barrier uh, is V of particle is outside this box is infinity. So these are the condition: Vx equal to infinity for x is less than 0 here this area, and x is greater than L here also the potential is infinite, and inside this box potential is 0, means it have only kinetic energy, so it will behave like a free particle between x equal to 0 and L. Now we solve the Schrodinger wave equation for different regions. So particle is in this region second, where potential energy B equal to 0 or U equal to 0, and in that case we have the Schrodinger wave equation del square psi plus 2m by h bar square E minus B psi equal to 0, or if we take in x direction only one dimension, it we can write delta 2 psi by delta x square plus 2m by h bar square E B equal to 0 for this region. So it will be 2me by h square h bar square equal to 0, and the boundary conditions will be required for the solution solving this second order differential equation. Psi x equal to 0 at x equal to 0 wave function is 0, and x equal to L at the boundary psi equal to 0. And now we have this equation delta 2 psi by delta x square plus 2m by h bar square E psi equal to 0, and if we take this term 2m E by h square as k square, where k is propagation vector 2 pi by lambda and it is under 2m E by h bar, and now this equation is equation number 2 becomes delta 2 psi by dx square plus k square psi equal to 0, and this is second order differential equation, and the general solution of this kind of equation is psi equal to a sin kx plus b cos kx. So we have to find out these coefficients a and b using the given boundary condition. So if we put the first boundary condition that psi equal to 0 at x equal to 0, so psi equal to 0 at x equal to 0 means put x 0 and psi 0 0, a sin 0 k plus b cos 0 k, and sin 0 is 0, so it will give us b equal to 0. So one coefficient is 0. Now we have psi equal to a sin kx only. So now this equation psi equal to a sin ax kx, and we have to use uh, the properties of wave function to eliminate this coefficient a, and for this we will use the second boundary condition psi equal to 0 at x equal to L. So psi 0 A sine k into L, and this will give us that A sine KL equal to 0 means A cannot be 0 because it is a coefficient. So sine KL will be 0 or KL equal to n pi. So this is the condition. If sine theta equal to 0, then theta equal to n pi. So KL equal to n pi, K will be n pi by L, and uh, we can find out the energy level using this formula, K square equal to 2me by h bar square. So E will be K square h square by 2m, or if we put the value of K also, n square pi square by L square into h square by 2m into 4 pi square. If we put h bar as h by 2 pi, then the energy equal to n square h square by 8 ml square. So this is the energy for the particle inside the box, and for n equal to 1, it is the lowest energy of the particle, and it is also known as the 0 point energy. So E1 will be 1 square h square means it is h square by 8 ml square. And if you see for the box, the energies of particle in state n equal to 1, 2, 3, 4, these values are discrete energies, not continuous as in classical physics. So for E1, E2, E3, we can put the different values. Now the wave function we have got psi equal to A sine n pi x by L, but here this coefficient A, we will have to find out this also, and we will use a condition that is known as the normalization condition, which is that the volume integral of psi star dv equal to 1. The probability of finding the particle in space is 1. So if we put the values here, 0 to L, A sine kx whole square dx equal to 1, A square sine square kx equal to 1, and limit is 0 to L for particle of box length L. So A square, so sine square kx can be written as, because we know one formula, cos 2x equal to 1 minus 2 1 minus 2 sine square x. So it will give us sine square x as 1 minus cos 2x by 2. So we can write, in place of this sine square kx, we will write 1 minus cos 2 kx divided by 2. And if we integrate then and put the limits, uh, we can find out the value of this coefficient A, and it comes under root 2 by L. If we put the value sine 2 pi 0, sine 0 0, and limits, and then now the final form of the wave function psi, which was in region second, or for the free particle, it was under root 2 by L sine kh n pi x by L. So this is the eigen function or the wave function. Okay, in this slide we can see the wave function and probability distribution for different states. We know the wave function like this. It is under root 2 by L sine n pi x by L, and if we plot it for n equal to 1, 2, 3, there are standing waves or sine waves. So wave function does not tell much about the particle, but the probability will tell the position of the particle. Suppose for n equal to 1, the probability of finding the particle is in the middle of this box, whereas for n equal to 2, the probability of finding this particle is at 1 by 4th and 3 by 4th. So this will tell us about the probability of finding the particle. Here is an example. An electron is inside a box of 0.1 nanometer, means it is order of magnitude of atomic dimension. So we can compare it, that electron is inside the atom, then what will be the its energies. So we will have to use this formula of a particle inside the box. Here electron is inside the atom, so we will use this formula, En equal to n square h square by 8 ml square, and m mass of electron is given, length is given. So if we put these values, the joule can be converted into electron volt. So En equal to 38 n square eV electron volt. So for n equal to 1, it is 38 eV, and for n equal to 2, it is 2 square means 4 into 38, 152 eV. So there are different energy states or discrete energy states for different values of n inside the box, or when the electron is inside an atom, it will have the discrete energies. Now we solve one example to find the normalization constant. If we have a function psi equal to a e raised to power minus 3x square, and we have to find this coefficient a, or normalization coefficient a. So we will use the normalization condition, that is uh, integral psi star dx is equal to 1. Finding the particle from minus infinity to plus infinity is probability is 1. So from here we can find out, we put the value of this psi a. Psi means this function a e raised to power minus 3x square. So it is a real function, so we can take the square of this. Complex conjugate of real function is the same function. So a into a square e raised to power minus, it will be minus 3 square 3x square minus 3x square, it will give minus 6x square dx equal to 1. So now we have to solve this integral, and for solving this integral we use the standard integration formula, which is, if this kind of integral is there, e raised to power minus ax square dx, and limit is minus infinity to plus infinity, then the value of this integral becomes under root pi by a. And here in place of this a, we have 6 is there, so we can use under root pi by 6. So the integral will be pi by under root pi by 6, a square into under root pi by 6 equal to 1. So from here we can find out a equal to 6 by pi to the power 1 by 4th, and this value is 1.18. So this is how we can find out this coefficient a in wave functions. And in 3 dimension case, just this will, here we have the solution for the x-axis only, or 1 dimension only, and in 3 dimension we will have to take care of other dimension y and z also. So in that case, under root 2 by a, under root 2 by b, under root 2 by c, it will give us under root 8 by abc, and sine nx pi x by a, sine ny pi y by b, similarly sine nz pi z by c. So we will have to take the all the 3 dimensions. And similarly in case of the energy also, E will be n square h square by 8 ml square. So then we will have n equal to nx square plus ny square plus nz square. So the in 3 dimension case, we have to just take care of the y and z axis also. Now the potential energy of a particle as it moves from one point to another point, it constitutes some potential energy step. Suppose here potential energy is 0, and in another region it have some potential V naught. So if this particle have higher energy than this potential energy V naught, then it can go to another region. But we will see that there is probability of going this particle from one region to another region using the tunneling phenomena, or transmission probability is there. So we will see, if in case of the rectangular potential barrier, if we have region 1 and then we have a barrier of height b naught, and this is region 1, region 2, and in between there is a big barrier of potential b naught. So bx equal to 0 for the region 1 and region 3, and Vx equal to 0 in between this region second 2. So usually according to classical physics, the particle, if the particle have energy E less than V naught, then it cannot go, it cannot cross this barrier. But using this quantum phenomena, or we see that there is some probability of this particle to tunnel through this barrier, and this is again due to the quantum nature or the wave nature of the particle. And the probability is given as transmission probability T equal to e raised to power minus 2a, this is the width of the barrier, divided by h bar under root 2 m. M is the mass of particle, b naught the height of barrier, and the energy of this particle is given. Then we can find out even E is less than this B naught, there is some probability of going this particle to in region, third region, where this barrier energy is less than this barrier. So this is only due to the wave nature of this particle of mass m. And this is also experimentally proven in case of the alpha decay, and also tunnel effect is in very thin layers. This can be proved experimentally also. Suppose we can see one example. If an electron have this energy is 6 electron volt and barrier height is 12 electron volt, and the width of this barrier A is given as 0.18 nanometer, then what is the probability that the electron will tunnel through this barrier? So if we use the formula for tunneling, T equal to e raised to power minus 2a divided by h bar under root 2m b naught minus e, and these all terms are given, and if we put all the values, then the probability or tunneling probability is around 4.4%. So this particle, even energy half of this barrier, it can tunnel through this, and the probability is there. It is not 0% but 4.4%. So it can go in uh, tunnel this barrier also. So if we in double the width of gap, then this probability will change. Here in this example, an electron is inside a box of zero point 0.1 nanometer. Find the first three energy eigenvalues and corresponding wavelength, de Broglie wavelengths. H is given as 6.63 10 to the power minus 34 joule second. So L is given, so we can find out the energy En equal to n square h square by 8 ml square, and from here we can find out E1 for n equal to 1, n equal to 2, and n equal to 3. We can find out the energies in joules, or if we divide it by 1.6 10 to the power minus 19, then it will be in electron volts. And to find the wavelengths, if we see for n equal to 1 state, this lambda by 2 is L, this length is L, L equal to lambda by 2, so lambda 1 will be 2L. Or we can find out also from this relation, lambda equal to h by p, and p equal to h by 2L by n. So lambda equal to 2L by n. So for n equal to 2, n equal to 2, we will have 2L by 2, means we have lambda equal to L, and for 3, lambda 3 equal to 2L by 3. So if we put the values here, then we can find out the lambda de Broglie wavelengths for different states. This is an example to get the probability for a particle inside a box L between the length 0.45L to 0.55L. So we have two limits. What is the probability of finding this particle inside the box, and we will put the limit as the probability is under root 2 by L into under root 2 by L. It will give 2 by L and sine square n pi x by L, and limit will be 0.45 to 0.55. And if we put all the values here, and we sine square n pi x by L can be written as 1 minus cos 2 pi n x by L, and if we put the limit, and for the ground state, so first for the ground state means n equal to 1, and we will find the probability after putting the limits here. After integrating this function and putting the limits, we get the probability for finding the particle in first state 0.198. For first excited state, the probability n equal to 2, and it is even less 0.0065, very small probability. So we, using this energy formula and wave function formula, we can find out the probabilities and energy of the particle as a wave. Now we have one another example, that wave function psi equal to a cos square x between minus pi by 2 and plus pi by 2. So first we have to find out the value of a, and also find the probability between 0 to pi by 4. So if psi equal to a cos square x, then the probability, or we have to use the condition for normalization to find out this value of a, minus pi by 2 to plus pi by 2 psi star dx equal to 1. So if we put it here, it will be a square cos to the power 4x equal to 1, and if limit is minus a to plus a fx dx. It can be written as 2 times 0 to a if fx is even function. So cos to the power 4x is even function, so we can write it 2 times of limit will be 0 to pi by 2 2 a square cos to the power 4x dx equal to 1. And to solve the integration of cos square x, we have to write it in terms of cos 2x. So we know a formula, cos 2x equal to uh, 2 cos square x minus 1. So from here we can write cos square x as 1 plus cos 2x by 2 and 1 plus cos 2x by 2 whole square, and then we can integrate it and put the limits. We will get these values a equal to under root 8 by 3 pi. And again for the probability we will probability is 0 to pi by 4 psi square dx and limit will be 0 to pi by 4. Then we can find out the probability. It will be 0.46 or 46%. So this is how we can find out the normalization coefficient and the probabilities. Again, this is the energy formula. Calculate the energy difference between ground state and fast excited state. So we will have to find out the energies E1 and E2 using this formula. And mass of electron is fixed, Planck's constant is given, and the L length of the box L or A is given. So just we have to put these values n equal to 1 and 2, and then we will E2 minus E1 will give us the energy difference between these two levels. This is again just an example to compare the energy levels for electron and one dust particle which have mass 10 to the power minus 6 gram. Electron have very small mass, so energies will be in measurable lengths. En equal to n square h square by 8 ml square, and if you put n equal to 1 2 3 like this, the energies will be 0.37 ev, 1.48 ev, 3.33 ev. Whereas for the dust particle, it is the energies are in 10 to the power minus 51 joule, or it is very small number. So for that's why we cannot see the discrete energy level in case of the uh, particles which have higher mass. So 10 to the power minus 6 gram is much higher than the mass of the electron. So this factor is important. So this kind of effects, or we can see this in subatomic particle like electrons or some very small mass when mass is very small. So thanks for watching, and if you are new here, then please subscribe to this channel, and your queries are welcome. Next video will be on density of states, and in last video I have discussed the Schrodinger equations, time dependent and time independent. So thank you very much.